Hi, I'm Shivaram. I'm a PhD student in the AMP lab, and today I'm going to be talking to you about some very recent research that we've been doing called Planck, which is a performance prediction engine for large-scale advanced analytics. This is joint work with Zhong Heng, who is an undergraduate researcher at AMP lab, and professors Mike Franklin, Ben Recht, and Jan Stoika. So if you take a look at some of the workload trends that we're seeing in data centers, we see a shift from some of the more traditional SQL-style workloads to some of the more advanced, what I like to call as advanced analytics workloads. So what do I mean by advanced analytics? So these include things like machine learning workloads that you might have heard talks of or you're going to hear talks about tomorrow. Machine learning workloads including, for example, like image classification, where you want to detect cats that are there on the internet, or speech recognition, where you want to talk into your phone and you wanted to identify what you're talking. But it's not just in the consumer space. Even in like scientific applications, we see a lot of these sort of big data, advanced analytics things, which are sort of becoming deployed more and more on commodity machines. So this includes, like, for example, the astronomy data sets, where we have like huge amounts of astronomy data being processed to detect stars or like supernova and stuff like that. But also like MRI data and other like mass spectrometry imaging, where again, large amounts of data are being collected in the physical realm, and we want to do a lot of advanced analytics and processing them. You might also see this trend shift if you've been coming to the AMP camp for the last 4 or 5 years, where in the first few editions of the AMP camp, we mostly had SQL and like ETL-based talks, whereas in this edition, we have a large number of like machine learning-oriented talks. So we've also seen a trend like this in the lab and in the kind of projects that we work on in the lab itself. One of the projects that I've been very closely involved with is this project called Keystone ML. You'll be hearing a talk about it in detail tomorrow, but at a high level, Keystone ML provides an interface or a framework for doing large-scale machine learning. So when we talk about advanced analytic workloads and we talk about like how we're going to like build them and how we're going to deploy them, one thing that's useful to understand is how do these workloads look? What are some of their properties? So this is an example Keystone ML pipeline that I've shown here, which is used, for example, in like speech processing applications, and similar patterns exist in other applications as well. So what happens here is we take some raw data. This could be images, or this could be like audio samples you have, or some text fragments you have, et cetera. And then we apply a series of featureization steps. So in this case, we are applying, for example, a cosine transformation, or we're doing some feature normalization after doing cosine transformation. And after doing some featureization steps, we typically use a learning algorithm. So in this case, we're using a least square solver, which is going to learn a model based on the training data that we have. And it's not just like one iteration of these things usually give us a good model. Usually we need to do a large number of iterations of these workloads in order to get a high quality model. So for example, some state-of-the-art work which builds a very good speech recognition model repeats the same pipeline that I've shown out here for around 100 iterations or so, and it could take many hours or so to run to get a very good model for the data set that we have. So if we take a step back at these workloads and try to see what is different in these workloads when compared to more traditional workloads, one observation that we make is that they're more numerically intensive. So they deal with more large number of like floating point operations and other like matrix or linear algebra operations as a part of like these workloads. They're also iterative, so most of them run a really large number of iterations, and each iteration is not just like one job. Each iteration could span many jobs. So for example, in this previous slide that I had, each iteration runs like a cosine transformation and a feature normalize, et cetera. So you have a complex DAG that's getting executed on each iteration. And finally, as a result of being iterative, a lot of these workloads are really long running. So to train state-of-the-art image recognition models or like some of these speech models, it may take like many hours or a few days to run, even on a large cluster of like hundreds of machines. And as a result of being long running, they're very expensive in terms of both time and money for people who are deploying these applications. So this is a trend that we see on the workload side, and on the system side, the trend that we see that has been predominant over the last 4 or 5 years, which is I guess less surprising for this audience, is this trend towards cloud computing. Many of the consumer space applications have already been deployed on cloud computing, and more recently we see even scientific applications being deployed on commodity cloud computing instances like EC2 or Google Cloud Engine, et cetera. So what happens when a new user who wants to execute some of these advanced analytics workloads goes to deploy some of this in the cloud? Before I get to that, there's also some recent survey on like Spark users that was done by TypeSafe, and it showed that more than 53% of the users actually deploy their production infrastructure on Amazon EC2, which is using Spark to run some of these workloads. So when some of these users go to EC2 and they want to launch their new job to run their machine learning job, what do they see? They see this really long list of like choices that they have in terms of the number of instances and the kind of instance that they can use for their job. So for those of you who've already seen this page in the Amazon website before, you'll realize that what I'm showing you here is actually not the complete set, and it actually extends for like 2 pages on either side of it. So on the one hand, the cloud computing providers have this view where they have a large number of instances with different types and different amounts of memory and CPU, et cetera. But on the other hand, the users have a different goal. Their goal is something like, I want to train my model within like 8 hours, or I want to spend like $200 and I want to train this model. So there's a sort of a disconnect between what the cloud computer systems are providing and what the users' goals are when they're trying to run these advanced analytics jobs. So this was the main motivation for this project, is to see if we can build a system that helps users deploy their advanced analytic applications better. So the first question that we asked ourselves was that, does this matter? Can you choose any of these instance types and will you get the same numbers? Like, does it even matter if I use like R3.extra large or 4 extra large and so on? So we ran a bunch of workloads across a number of instance types and tried to do some benchmarking to figure out what the performance properties were. So here we used a commonly used linear algebra kernel, a QR decomposition algorithm, and we ran it on machines of different sizes of the same kind. So here we used either 16 R3.large instances or 8 R3.extra large instances, and so on till 1 R3.8 extra large instance. So they're all normalized in terms of the amount of memory and CPU available, and we're running the same workload on all of them. The animation for this sort of like messed up how this looks, but what you can see in the graph behind this is that there's actually a huge difference in performance, even though we're paying the same price per hour across these instance types. And more surprisingly, what we found was that the smaller instance types, like the 8 R3.extra large or the 16 R3.large instances, actually finish the fastest. The axis here is actually showing the time it takes to run this computation. So this was initially a surprise to us, and so we did some more work in trying to figure out why this is the case. And some more detailed benchmarking of the instances themselves showed that you could actually get a lot more memory bandwidth, which is what these applications were sensitive for when you use a large number of smaller instances. So does this remain the same? Like, am I going to use the same R3.large instances for all kinds of workloads? It's not quite that way. So we ran another benchmark, which is a matrix multiply workload that's more communication intensive. And in this case, we found that actually one big machine actually saves you a lot of time on communication, and you can actually get much better performance on this one giant R3.8 extra large machine. So there is a factor here based on what your application is doing. Different kinds of instances might be more appropriate for it. So that's on the instance type that you want to choose. What about the number of instances that you should launch? So in this benchmark, what we did is we fixed the R3.4 extra large instance type, and we kept increasing the number of instances that we launch. So we went from like 2 to 4 to 8 and all the way to like 64 machines for the same workload. So initially, we see some benefits. So when you go from 2 to 4 to 8 machines, the running time halves for each of these things, and the price remains kind of constant. So you're actually getting like double the performance while you're paying like extra money for these instances. But after 8 machines, you see the performance sort of like flattens out. So when you go from 16 to 32 machines, the running time hardly changes, but you've now paid like double the amount of money for renting these 32 machines on your instance. And in some cases, we even see the performance goes worse. For example, like 64 machines performs worse than 32 machines. So you're not only paying more money, but you're getting worse performance than you could have. So the goal of this work is to say that you're given a job, and it's like input description. Can we help users figure out what is the optimal set and what is the number of instances that they should be launching for their particular job to complete? And to do this, the core insight that we have is that if we can develop a performance prediction model, that when you're given the job, it can predict the amount of time that it's going to take for different configurations that you have, then we can quite easily perform these like suggestions to the user on what kinds of instances they should choose. But building a performance model is actually quite tricky in this case. So for one thing, we don't know much about the job. It's like sort of a black box that has a lot of user-defined functions and doing a lot of complex things. But also, on the other hand, to build the model itself, it could be expensive. As you saw, you have like 20 or 30 instance types, and in addition to that, the number of instances you can vary across a large number, from like 2 to 100, and so the number of possibilities that you have is like many thousands of possible cluster configurations for each given job. So the key insights in this work are, can we make it really cheap to build a performance prediction model while also still being accurate for a given user-defined job that we're going to run? Some of the main insights in our contribution here is that we try to build an end-to-end performance model from going from like the input to the complete model being built. And the key insights that we use is that most of these applications we find are very regular in behavior. And by regular, what I mean is that if you take a very small sample of the data and you run the application on it, you can try to infer its performance properties by looking at what it's doing on the small sample of data. So we exploit this fact, and we try to run the application on small samples of data and measure its performance and try to then predict what will happen when you run it on the larger sample of data. And finally, we also exploit the fact that these applications are iterative. So even if you run a few iterations of the application, you can try and figure out how its performance is going to look, and using that, we can again extrapolate to larger number of iterations. So let's see how we actually go about doing this and what is the science behind this performance model that we built. So one of the first things that we look at is like, how does the job look? So what is the structure of the job that we're going to be executing? Once again, the animation here it hasn't come out right. But at a high level, what we found was that there are a small number of patterns that keep getting repeated in these like jobs that we see. So some common patterns that we see are these kind of like one-to-one patterns, which as you add more and more data to your thing, you get a one-to-one mapping between different tasks that are executed in the DAG. Some other common patterns we see are a kind of a tree aggregation pattern, where if we start with n partitions, then you have a log structured tree towards like aggregating towards one partition. This is, for example, found in a lot of the aggregation-oriented queries that people run. And lastly, we also see some linear patterns, where if you have n partitions of data, all of them are communicating to one machine. So this is, for example, like a broadcast variable would have like this linear pattern, or even some of the reduce operations that you might run in something like Spark will also have this kind of like linear pattern. So the key insight with seeing a small number of patterns is that we can actually build a very simple model if we're able to capture these patterns in our performance model. So what do I mean by that? So what I mean is that we can express the total time taken by the application as a sum of a number of terms, each of which capture one of the patterns that we saw in the previous slide. So I'll walk you through this a little bit more slowly. We have two variables here on this slide. The first one is input, which is the amount of input that we use, or the sample that we use to actually run this job. And the second variable we have is the number of machines that we use to actually run this job. Given these two variables, we can write out a performance model which looks something like this. The total time taken is the sum of a constant factor, which is the time spent in serial execution, shown here as A, plus a linear term, which is shown here as input by machines, that models the linear computation that goes on in parallel across all of the machines that you have. And then two terms which capture the communication patterns we saw previously. One to capture the tree communication pattern, which scales as log of the number of machines, and the other which scales linearly in terms of the number of machines. So the high-level intuition is that we can run this job on some samples of input data. We can collect some training data using the samples that we run, and then we can train a model to fit a model to learn values of A, B, C, and D for this equation. And once we know A, B, C, and D, given a new amount of data size or new number of machines, we can plug that in here and get an answer. So this is the high-level approach that we're going to do. So the next step that we did is, does the model that we saw in the previous slide actually match the real world? So we took a look at all of the MLlib applications that ship as a part of Spark, and we tried to classify what are the sort of patterns that occur in these applications. So here I show you the patterns that happen in GLM regression, k-means, naive Bayes, PCA, and so on. And we see that the few terms that we had in the previous slide are actually able to capture almost all of the patterns that we see in these applications. So this was very good to know for us, because the model looks really simple, and we wanted to know if real-world data actually matches the model that we came up with, and we used the MLlib repository to validate our assumptions. So what next? Are we done? I mean, we have a model, we can train a model, and we can learn it, and it'll be all good. Well, there is still a problem, and one problem is that we need to collect some training data to build this model. And as opposed to other cases where you have a big data problem, we actually have a small data problem here, in the sense that we actually have no training data to start with, and collecting any training data is expensive, because you have to actually go to EC2, run a job, which takes some time and money that the user could have used to actually run their original job. So we had to figure out a way to cheaply collect enough training data so that we can build a good enough model, and for it to not be too expensive. So the approach we take here is that we look to statistics, and we specifically look to a branch of statistics called experiment design. Now, the roots of experiment design come from a time where collecting data for doing real-world statistics was actually very expensive. Like, you can think of it in the 50s or 60s, agriculture required like a lot of statistical analyses, and it was actually expensive to collect data and took a lot of time to collect data in the real world. And so the high-level idea behind experiment design is that if you're going to build a model, which looks similar to the model that we had before, which is a linear model, you can use experiment design to figure out what are the important coefficients where you need to collect data for your model to be accurate. So to give you an intuition of how this works, the linear model that we had before is expressed here in this formula yi equals ai transpose plus wi. And the insight here is that the error in this model, or this model is given by the covariance matrix of the estimate that we have, and that estimate is actually independent of the actual model parameters, and it depends only on these coefficients AIs. And the intuition being that if you have a lower variance, then you have a better model. So given that insight that we get from looking at the model that we're building, we can actually formulate a small optimization problem where we want to minimize something related to the covariance matrix that we had. So in this case, the trace of the covariance matrix. And we want to find out which configurations actually help us minimize the trace of the covariance matrix subject to some constraint. So what is the constraint that we have here? The constraint is we want to minimize the cost. So you set a budget of like, I want to use this much time in order to do my training. And then you try to find out which are the configurations that I should choose so that I can actually finish training within that budget and yet still minimize the amount of the variance that my model has. So having set this up in this way, we can actually just use an off-the-shelf solver like CVX and get what are the optimal configurations for the specific problem that you have. So just to take a step back, the workflow that happens here is that we give this procedure a range of machines we want to explore, like say between 1 and 8 machines, or between 1 and 8% of the input data. And then we feed in this range of data points that we can choose from to the CVX solver, and it returns back these red dots which show like, oh, you should collect training data at 4 machines and 1% input, and at 1 machine and 2% input, and at 2 machines and 4% input. So this helps us formulate the jobs that we'll actually run for training. So let's just summarize the whole procedure here that we use for performance prediction. So we have a job that the user wants to run and some input data that the job is going to use, and we feed both characteristics of both of them to the experiment design model that I showed before. So that tells us how to collect training data, and then we run some small training jobs on an EC2 cluster. We use a few iterations of the job to do the training, and based on the training data that then we collect, and we build a linear model based on that. So putting it all together, how well does this work in practice? So the same Timid pipeline that I showed you earlier on, right at the beginning, the Keystone ML pipeline that is used for speech recognition, we collected training data up to 16 machines, and then we tried to predict its performance on 45 and 64 machines, respectively. So what we saw was that the prediction error is actually pretty good, and it's within like 15 to 20% of the actual running time when you run it on 45 or 64 machines. More interestingly, what we found was that the training was pretty cheap. So it took only like within 5% of the overall runtime for us to actually train this model. And so we can actually use this prediction as a low overhead prediction for the jobs that we're going to run. We also tested it on all of the MLlib benchmarks that I had shown you before. And we found almost similar behavior where the error was within 15 to 20% of the actual runtime on 45 and 64 machines. And finally, we wanted to work through an example where we can show how the performance prediction is able to catch some non-intuitive behavior that you wouldn't probably expect. So that timid pipeline, when we scale it across a large number of machines, we see the scaling behavior where it sort of like flattens out across over time. And the model that was learned using up to 16 machines is shown in these red dotted lines here. And it sort of captures how and where the performance plateau happens. So in this case, we can see that, so the zoomed in version of the left-hand side is shown on the right-hand side. And we see that it's actually fastest when you use like 40 machines or so, instead of using 120 machines to run the same workload. And at 40 machines, it takes around 57 seconds. And after that, it actually increases to like 60 or 65 seconds. And this is for one iteration of the job that I showed you before. So hence, the overall takeaway message is that using the model that we built, we're actually able to figure out what is the optimal number of machines that we should launch for a given workload. So what's next here? So this is some very recent research we've been doing, and what we're trying to do is put together an open source tool that you can play around with, and that you can give it your own jobs and see what are the performance predictions that it makes. We're also trying to run many more workloads on this. So after this, you're going to be hearing a talk about ADAM, which is this genomics framework. And we've also used that to see how well can we predict the performance of those jobs. And also, we're planning to run it on large traces of other like machine learning queries that we have. And finally, there's also some very interesting research that we're doing on trying to predict when the model will not work. Like, let's say you have a job where the model does not fit your job. Can we actually tell you that the model will not fit your job and sort of like prevent giving you wrong answers? So I'd like to conclude by saying that with this shift in trend towards advanced analytics applications, there are a lot of challenges in deploying them to like commodity cloud computing infrastructure that we have. As a part of this work, we specifically looked at building performance models so that we can do performance predictions with low overhead for these workloads. And one of the artifacts that we're going to build as a result of this is an open source tool that you can use with an Amazon EC2 cluster. We're always interested in like listening about more real-world workloads that you might have, or any other traces that we could use for driving research and like evaluating how well our research works. So feel free to shoot me an email if you have anything like that. And with that, I'll conclude and take any questions. Thank you.